Hello and welcome to another edition of the 7th edition of the Nasm Essentials of Personal Fitness Training Manual Information. This is Chapter 8, and we dive into exercise metabolism and bioenergetics. Another one of those very important types of lectures here because, energy systems are going to be critical for you to understand what types of basically, exercise programming that you would do based on what that person is trying to achieve, whether it be cardio-based, aerobic, or whether it be anaerobic, being more glycolytic or more ATP PCR, which we'll talk about in a little bit. And obviously the bioenergetics piece, more fuel-based, to know what you're going to be using for fuels as you go through. Okay, so again, just like Chapter 7, which was the Human Movement Sciences chapter, this is just as valuable, although not as long. This is very straight to the point, so it's going to be, I don't want to say this is going to be a quick lecture, but it's going to be one that gets right down to it, and you can basically understand each component very quickly along with what's in your book. So again, what do we want to make sure of? We want to make sure that we understand that foods, carbs, fats, and proteins, your macronutrients, are going to be the energy. Well, they're going to be the food source that will provide you the energy that is needed for whatever you're trying to do. So that food that you bring in will go through chemical reactions. It'll then be converted into what we call ATP, adenosine triphosphate. That is one adenine and then 3 phosphates. That's how it's broken up. And ATP's job is to be broken down anaerobically, like we said, or aerobically, so short bursts or long duration, to supply us with what we need to make sure that ATP is constantly supplied, or it's to give us an explosive all-out effort that we might need. So the bioenergetics piece, again, is the study of energy in the human body. So we know that energy is needed for everything. We know it's needed just for daily living. We know it's going to be for us in particular for exercise and for other things like with amino acids, for example, with recovery, but carbohydrates are there too and fats are there as well. So it's always part of that. So that's part of the process. So again, bioenergetics is basically understanding how we use energy correctly throughout the system. Now, metabolism, on the other hand, is the chemical reactions that actually occur and really are done by the body so that it can be maintained. So when we talk about metabolism, it's body maintenance. It's, and so everybody always assumes your metabolism is based on your calories. Well, it is. But the factor is that with metabolism, it needs to be understood that it's about how the body maintains itself more so than anything else. Versus exercise metabolism, which is more important for, obviously the fitness piece and for the other aspects of, recovery and other physiological demands that we have. So that is one thing that we want to make sure we're very clear on with that. So, to basically kind of get a little bit more of this, we want to be able to understand that, with energy, it's understanding the energy component of everything. So we have to go by the first law of thermodynamics with this, in that energy cannot be created or it cannot be destroyed, but it's going to be converted from one form to another. So that is how we always work with ATP in our system, is that we don't necessarily lose ATP. It's that ATP is broken down and then it is built back up. All right. And that's really how we work on, I don't want to say it's more conservation, because you're always building, anaerobic, or not anaerobic, excuse me, catabolic, anabolic, breakdown, build up, and that's kind of how we flow through that process. So what we want to make sure of, again, is proper macronutrients, carbs, fats, proteins that come into our system. And by making sure we get the right amount of them, will supply us with the right amount of energy. Now, on one hand, you got to be aware, the bottom 2 bullet points, that, consuming more energy than you actually expend could potentially lead to weight gain. Now, we're talking about expenditure here, not saying it's all just about body weight or the like. So if you're a very active person, you're going to need more calories. And if you don't hit that calorie mark, you'll end up with the second bullet point, where you're going to expend more energy than you actually consume. So for exercisers, you're like, well, why am I losing weight when I'm really not trying to? And that's the main point there, is that you're just not getting enough in your diet. And so by not, amongst other things, but, it could potentially lead to that. So we have to be aware. You consume more than you expend, you have a potential to gain weight. You expend more than you consume, you have a potential to lose weight. So again, it's not built in stone, it's guaranteed, but for the most part, that holds true for almost everything, and for almost every, occurrence. So what do we got to be aware of with the fuel part of everything? Well, we got to be aware of what our substrates are. So again, carbs, fats, proteins. All right. Your carbohydrates, you're talking about glucose and glycogen. Glucose being what's, the main source of energy. All right. It's going to be, versus glycogen, which is the storage form of glucose that you find in the liver and the muscle. Once that is converted, then that would be glucose inside of the bloodstream. All right, so that it can be used for, like it says here, proper brain functioning, and be also converted inside of the muscles to be used for energy. Okay, for, like it says here, higher intensity activity above rest. So, that's really the main part of that. So, then you get your fats. Well, fats can be used for a lot of really important things that we'll get down to in a little bit here, but predominantly, we're talking about fats during low intensity and rest, and then proteins are good for recovery. Those amino acid chains are going to be good for recovery, building. All right, so that's all part of this process so we can maintain regular life, regular metabolic transfers, regular energy output. Okay, all of those things are going to matter. So we have to be aware of what we're talking about in terms of level, okay? Level of energy use. Now, Nasm is really big on these two terms at the very, very, very bottom, ventilatory threshold 1 and ventilatory threshold 2. When we talk about VT1, okay, like it says there, it's the point at which the body uses an equal mix of carbs and fats as fuel sources. That is predominantly during lower intensity types of exercises. And then when you start getting up above a certain threshold, VT2 would take over, and the primary fuel source for that would be glucose. All right. So, again, it just depends on how hard you're working or if you're at rest, but typically VT1 is more carb fat, or VT2 a little bit higher intensity, and building up to max levels, we're talking about glucose being the predominant. Like I said before, fats coming up next. So here you go. Fats, their storage form, okay? Their storage form is triglycerides, all right? But the breakdown of those triglycerides is into fatty acids. And those fatty acids are what we would need to be released into the bloodstream to be able to be broken down so that they can be used as energy, so that they can, again, be used with, anytime you have fat, it must be used with oxygen to be able to create ATP to use aerobically. All right. So even during recovery and rest, we're talking about aerobic processes. All right. Rest and recovery is aerobic. It's an aerobic process, which means oxygen must be present even though it's low intensity. Okay. So again, what are major, not sources, but, we want to take the main sources, the healthy sources of fats, use them, but they are really important for fat soluble vitamins. They're really important for skin health. They are a very important process for energy stores in the body. Even though we don't like to have stored body fat, as long as you're carrying around the right amount and the right amount is also in your blood, then that is okay. Okay. So we have to just be aware there's saturated and then there's also unsaturated. Is one better than the other? Yes. We want to think more about the unsaturated components, but understand that with the saturated components, that's more animal products, more animal, and obviously animal based, which is dairy. So again, is dairy 100% necessary? That's a topic for another point in time, but understand that's where the saturated part comes from. Okay. So again, there's that part there where we talked about if an individual is working at an intensity below VT1, then free fatty acids are your primary fuel source. Okay. Fat, very importantly, carries a lot of ability to create a lot of ATP. It is very, what we would call, obviously fat is very, it's not so much that they're nutrient dense, but they are very caloric dense, but fat is also very energy dense, which is okay. 9 kcals that we have, 9 calories per gram that's put out there. Proteins, on the other hand, they're amino acids that usually are attached, but they're amino acids that have a linkage, that have a connection point with peptide bonds. And they're, again, what's their main function? They're building blocks of body tissue. All right, we know that. They are the building block. They are the recovery piece. They are going to basically sew everything back together. Now, within our system, we got 20 different types of amino acids, 9 of which are essential, which means we have to have them in our diet. And then 11 are non-essential, which means our body produces them. And it's not that we necessarily need to have more of them, but just understand that with a proper diet, we wouldn't need to take like supplemental non-essential amino acids. So, what are we saying? With a proper diet, we can get a complete protein which contains all the amino acids, but just understand that non-essential means that they're in your system already, and that maybe you might need a little bit more here or there for a particular one, but we don't have to go supplementing like crazy for that. All right. So one of the things we want to make sure about proteins, though, is that, like it says in the bottom, if there's a negative energy balance, meaning that you're very low on your calories and you're still expending a lot of them, amino acids can get to the point where they will be used to be broken down to basically be converted into ATP as well. But that's usually during very, very negative energy balances. Think about the end of like an Ironman competition or in times of starvation. But also think about very, very intense workouts too. That can happen as well. The other thing that we have, in terms of fuels is what we call ketone bodies. Now, they are basically produced by the liver, and typically they are produced by the liver when we realize that there is a high level of fatty acid breakdown or fatty acid oxidation. All right. So what happens here is that they can be broken down inside of the mitochondria. Okay. They're inside of the mitochondria. So if that's the case, then we know that anything that's broken down into the mitochondria is an aerobic process, meaning oxygen is required. So we can break down ketone bodies. We can break them down to be put and produced ATP as necessary. Okay. When's the time that we usually have that happen? When carbohydrate stores are low. Okay. And so what happens is those ketone bodies are produced, they're made, and then like it says here, and they're used alongside what we call gluconeogenic glucose to help make up the deficiency. So glucogenic, okay, or gluconeogenic, what we're saying here is we're producing new glucose, but it's going to be stored as glycogen. So ketone bodies are produced, and then alongside of made glucose that's converted in our system, not that is brought in by food, because remember, we're under a low carbohydrate condition here. Okay, so what that can lead to is ketosis. It doesn't mean it will, but it can lead to ketosis, which is basically a rise in those ketone body levels. Okay, so again, how are we going to get there? Ketogenic based diets, low carb diets, restricting overall calories, that can be very, very low. Also, if we took in what we call exogenous ketones, exogenous meaning we're going to take it from the outside, put it in, so things that we consume. All right. And then also, which can become very scary if it leads to it, but like it says here, when there's a lack of insulin produced, like for a type 1 diabetic, or if there is a substantially large amount of insulin resistance, we could produce ketone levels or increase our ketone levels. But that typically, if it gets to a point of severity, can lead to what we call ketoacidosis, which basically means that, with anything that is acidosis, it means that we are more, we're basically saying we're more acidic. Our balance within our body is off, and because we're producing too many ketones, we are going to become, we're basically going to become not toxic, but you will become overabundance with ketones, and that changes the blood chemistry. And that can lead to some, complications with health. So ultimately, what are we talking about here in terms of how we break all these food things down? Well, or we take our food products and we are going to convert them to ATP, which is on your left side. Okay, your adenine, okay, mixed with your 3 phosphates, which is we call a high energy bond. It has a high energy bond in it. When this is actually broken down, it will create what we call ADP, which is, if you look at the 2 P's there, that's a diphosphate, adenosine diphosphate. And then what you have is what we call an inorganic phosphate, which means that we've separated ATP into ADP. It's created energy for us to be used. And then what you end up with is a phosphate. And that phosphate's job is to go around and reconnect with a creatine, and then take this whole process and circle it back around to recreate ATP again, break it down, take that phosphate, build it back up again by finding a creatine molecule. And that constant process happens over and over again until the body realizes that it's so low on ATP stores that it'll tell you to slow down or stop. So what we end up with is a term called phosphorylation, okay? And like it says here, it says it's the addition of a phosphate group to a molecule. And like it says, it's like a transfer of a phosphate group to an adenosine diphosphate, which is basically this process right here. Broke it down. Phosphorylation will occur when a phosphate is built back up with an ADP plus a PCR. So if we looked at it from a standpoint of, equation base, if we saw that it's ADP plus what we call a phosphocreatine, which is a phosphate plus a creatine molecule, equals ATP, all right? And then what it's going to have is a plus a CR. Now this creatine will go off on its way and it'll separate, and that'll leave ATP left to then do its job again to circle back around, break it down for more energy sources. So that's phosphorylation. Okay, is that transfer component of a phosphate to something back into, like we said, ADP. So how do we do that? Well, we do it in 3 different systems. Okay, the ATP PC system or the ATP PCR system. We have what we call the glycolytic system, or what we would call anaerobic glycolysis. And I'll just kind of put that down here so you can see that, anaerobic glycolysis. And then you have what's called the oxidative system, or oxidative phosphorylation, or the aerobic system. So 2 anaerobic bases here, 1 aerobic base there. So depending upon intensity levels is really going to be what is going to occur to make sure we meet the demands that are necessary. If you look right here, the red is your ATP PCR system, seeing that we stay predominantly in the ATP PCR system for about 10 seconds and then we kind of fall off a lot. So what happens is at a certain point at about 15 to 20 seconds, you can see here that before this ATP PCR system crashes, you will actually, and if it's going to be prolonged, you'll see that the short term, or what we call anaerobic glycolysis, will take over. That means that this is only using ATP as the primary source, and what it's doing is it's taking the PC or the PCR, like we just said, and using it to rebuild ATP. There's no need for carbs, fats, or proteins at that time. But when we get to that short-term base, that's when we start really having to use carbohydrates. And what happens with carbohydrates when we break them down is they'll eventually, depending upon intensity, would produce high levels of lactic acid. Okay? And so what eventually happens is after about 2 to 3 minutes, we start seeing that the aerobic system really starts to take over, and that will take you for as long as you're going to go. Like, again, a marathon, fast marathon, 1 hour, 59 seconds, and I believe it's 59, and I think it's 1 hour, 59 minutes, and I think it's 48 seconds is the record. So, and it'll take us for as long as we can go. But understand that long-term energy systems, again, we're using carbohydrate breakdown in the presence of oxygen. These other two where there's no oxygen required, okay? But this will take, glucose breakdown in the presence of oxygen, or fat breakdown in the presence of oxygen, or protein breakdown will give us the energy that we can continuously move on. So again, intensity changes that. ATP PCR system, very high intensity. Short-term anaerobic glycolysis, that's going to be, intensity is going to be a little bit lower, but it's going to be just as important, because we're going to need that. But the limiting factor for that would be lactate or lactic acid. And then again, way lesser of an intensity, you're talking about the long-term energy system, but that's why you don't burn out as quick, okay? So that's why we can sustain, longer durations of running, jogging, biking, rowing, for a long period of time, because we're not as intense. Because if the intensity went up on those from a run versus a sprint, you're going to be down here on the left for a sprint, and you're going to be up on a jog and run over here on the right with the blue color. So again, there's your ATP PCR system. All right, see how we basically just said adenosine diphosphate mixes up with a creatine and a phosphate, and it adds back, and like we said, it creates another ATP and another creatine, and then that will come find another one, and another process will happen. The creatine will find another phosphate. It'll keep happening. Now, the ATP PCR system will last for roughly 10 to 15 seconds at max. All right, so think of the activities that you could do in 10 to 15 second bursts, and that would be your ATP PCR system. But you have to have ample recovery for this process. Okay, again, high intensity, short duration exercise. Anaerobic glycolysis, like we said, because it's anaerobic, it takes place in what we call the cytoplasm. Okay, so the cytoplasm, you can see in this diagram down on the bottom left here, is all of that basic inside portion of the cell. Now, mitochondria is where we would find the aerobic bases. Okay, now carbohydrates are broken down to glucose. Through glycolysis, they will make ATP, but that glucose gets broken down to what we call pyruvate, and that pyruvate is what is that, what the byproduct of that pyruvate being made is lactic acid or lactate. Typically here we're about 30 to 60 seconds of pretty high intensity effort that will get us to that point. Anything above that means that we have to lower the intensity and move into the aerobic. Now, what are we saying here? Main fuel sources is carbohydrates without the presence of oxygen will recreate ATP over and over again. Okay? But again, like it says on the bottom, if oxygen cannot be delivered fast enough, pyruvate is going to make lactate. And at that point, that's when you start feeling that burning sensation in your legs and your arms, depending upon what movement you're doing. And then the oxidative system you can see here, or oxidative phosphorylation, that is going to be, again, an aerobic process. Oxygen is going to be present. So let's go right to the middle. Main source, carbohydrate. Carbohydrates are broken to glucose, which we talked about. So through glycolysis, we make pyruvate, and we know we're making lactic acid because it does. But understand that our system, when it's not as intense, can remove that lactate or lactic acid and use it as a fuel source more so than it'll use it as that burning feeling. So what we call that is buffering. We are able to buffer more because we're not producing as much because the intensity is not as high. So we make pyruvate. Pyruvate is broken down to a what's called acetyl-CoA or acetyl coenzyme A. It'll get shuttled over into what we call the citric acid or Krebs cycle, where it makes ATP. And that citric acid cycle is going to produce electrons by way of hydrogens, and those electrons will get broken down into more ATP because it's always moving through. So the electrons that are built off of the hydrogen production, which is from the byproduct, the waste byproduct of that breakdown inside of the citric acid cycle, those electrons will be used to go down a chain that makes a cascading type of events, and therefore it'll produce ATP. So for every 2 ATP, you get 3 ATP produced. And if you're making enough hydrogen, that means you're getting enough byproduct of electrons at the same time. So all of this happens with carbohydrate breakdown. On the other hand, fats are broken down to fatty acids. They have to go through what's called, not glycolysis, they have to go through what's called beta oxidation. And when free fatty acids are broken down through beta oxidation, they'll get shuttled over as acetyl-CoA, again, into the citric acid cycle, where, again, the electron transport chain and the citric acid cycle will produce a lot more ATP. Carbohydrate breakdown, you get about 32 to 36 ATP produced per molecule. Fat, you get, basically, for one fat molecule, one triglyceride, you will get 460. From fatty acids, you get about 441. And then with proteins are broken down through what we call deamination, and they are then would get shuttled into as acetyl coenzyme A very quickly. There's a lot more that go into protein, but this is the baseline for that, where citric acid cycle, electron transport chain producing ATP. The issue with protein is there's not a lot of energy in it. So that's why people feel fatigued when they're under starvation, because the protein just don't make enough, they don't produce enough ATP to keep us on a higher intensity. So that's why you see performance drop severely when people run out of carbohydrate and fat stores and they rely just on protein. So just like anything else, we said, what is the major factor that we have to pay attention to? And that's intensity, okay? Anything above, like it says here, higher intensity activity, anything above ventilatory threshold 1 will have lower durations, but carbohydrates are your primary fuel source. Lower intensity activities below ventilatory threshold 1 mean higher duration, but that also means that fat is your primary energy source. Now we're talking about low intensity. So understand that VT1 is a very low intense based type of threshold. Okay? But just understand that you're never, and that this bottom line is one of the truest statements that you could ever read, is that you're never in a 100% of one energy system at any given time. Even when you're doing high intensity back squats, you're never in one energy system. You will never see it as 100% of that system. There is always still some other process outlined in the background. Okay? So moving through, what ends up happening is, with aerobic base, you can see here, and there's a lot of factoring that comes into play. So pay attention to your A, your B, your C, D, and E. Okay? But understand that in the normal sense, our body is it wants to always, and for aerobic, it wants to always maintain what we call a steady state. And by doing that, what it does is as you come up from resting levels, if you follow the cursor over here, you'll notice that that A part, that's your rest. But as you start coming up, what you're doing is you're going through a transition period, and this upward motion is anaerobic. So you're really kind of clunky, kind of chugging along here, and eventually you start to have heart rate level off, using carbohydrates leveling off, lactic acid is being buffered correctly, and a lot of these physiological methods are just becoming more regulated, and you're able to sustain. That's why, like, the first, depending upon your fitness level, but that's why people in the first 5 minutes or so, they don't always feel the greatest until they get to like post 4 to 6 minutes, depending upon fitness. And so what you end up with in the C part is your true steady rate, and that can last for as long as you need to go for. They cut it off at 8 minutes here because they're saying it's an 8-minute exercise, but it could go longer, depending upon what you're doing. If you're going for a 30-minute jog, that steady rate will stay pretty ebb and flow and stay very consistent across that 30-minute time frame. And that's, again, everything is more stable. Your oxygen consumption, so your VO2 is pretty handed there, and that's what makes a big difference in you maintaining your fuel utilization. So then what happens though is we see this D part right here, this D and this E. Well, the D of this is what we would call, that's the first stage of your recovery. And what we call this is EPOC, or excess post-exercise oxygen consumption. Okay? And what happens here is we have to understand that this bottom number, this bottom A, is your resting period. Understand that we stay above that resting threshold for as long as it needs for our body to take. So what we're doing is we're burning additional calories, but we're utilizing additional oxygen to get us to recover. So what we're saying here is our body has to be elevated and enhanced above resting levels so that it can then lead to the recovery that it needs to. So eventually what will happen is with that oxygen consumption, you're basically resynthesizing ATP to get you back down to baseline. Okay, and that will help you also remove things like lactic acid and other waste byproducts like carbon dioxide that would be in your system at that time as well. So during intermittent work, the problem that we run into is we end up having no steady state, okay? And that becomes a challenge. So if you look, intermittent work usually, like it says on the bottom there, intermittent work cycles between B and D. Okay, so you're not really hitting a steady rate. You're kind of just in and out of that B and D. Now, if the C part takes over, then what ends up happening is you're going to start becoming more aerobic. All right. So typically what will happen is your intensity is going to be elevated, but then you have to come down with your intensity and like an ebb and flow. That's what intermittent work is. High intensity followed by lower intensity. So what happens is you never hit that steady rate because your heart rate, your oxygen consumption, your breathing rate, all of those things never regulate to stay steady. So you go BD, BD until finally, if you slow down and bring down the intensity, then you could stay in that C pattern, which is that steady rate. But like it says here, if the prior bout of higher intensity work is less than 1 minute, meaning that it was majority of the ATP PCR system, then your recovery will need to be about a minute or less so that you can maintain that flow of intermittent work. But the longer your rest period, the more recovery you have, the lower that, that means you can get more intensity on the next bout. So it just depends on what you're trying to achieve there. So again, saying that you're not always in one fuel source or energy system, you can see here that in 10 seconds, ATP PCR is majority. There is some glycolysis that's in there, and there is a little bit of oxidative. So although you think that you're completely elevated that way, and you'd be way higher in this purple realm, that's not always the case. Same thing here with your 30-second mark. That's more glycolysis, but you can see here that majority is glycolysis with some ATP PCR and oxidative forms. 2 minutes, again, you're starting to really transition from being about 50% oxidative to 40-45% glycolysis, and a little bit from the ATP PCR. And then lastly, when you're getting above 10 minutes, it's majority aerobic or oxidative system. And you can see it's very minimal ATP PCR. And that's really what it comes down to. So again, what are our fuel systems? Like we said, phosphocreatine on the first one, glycogen and blood glucose for the second for glycolysis, and then pyruvate and free fatty acids are predominant for the oxidative, along with your carbohydrates as well. But you can see the difference in your intensities. You can see how maximal ATP production, and that's why you have to slow down as you get, you have to be less intense as you get more aerobic. Time to exhaustion is dramatically different, and there's your limiting factors there. ATP PCR stores are going to be limiting. Lactate and CO2 accumulation is going to be your limiting factor because they're going to build up very high. And then insufficient oxygen, if there's a high level of heat or there's muscle fatigue, would be the main reasons why you would stop for those. But one of the things we want to understand is that, we're always talking about the fat burning zone. And typically when we talk about the fat burning zone, we're talking about low intensity and you'll burn predominantly fat. So look at what happens here. If you were to take a 20-minute workout and go low intensity only, yeah, you're going to be predominantly fat burning. Great, that's awesome. But understand that you're only burning 42 calories from fat, which is about 70% there. That's great and all, but again, we're getting about 30% from carbohydrates for a total of about 60 calories. Now, if you built that from a lower intensity to a moderate intensity, which is still not as intense as max, obviously, then look what happens. You're about 50-50. So if you're going to burn in that 120, for that 20 minutes, you're talking at moderate intensity about 120 calories. You're getting 50-50, 60-60. You're getting 50% of fat burning calories and 50% carb burning calories. And you can see here it's still higher in both sections, and it's an overall higher calorie burn. So it's kind of like a no-brainer as to where you want to sit with that. Okay? So we always want to be aware that, is there a fat burning zone? Yeah, but is it the best bet for you? No. It's better off burning total calories where more of them will be contributed to fat overall if you're using yourself the right way. Okay? So try to avoid using that fat burning zone as a talking point when we can really say, no, we want to work moderate to moderately intense and get more out of it. So really what happens, we have to make sure that we, again, do we meet our daily needs? Are we under our daily needs? Are we over our daily needs? And that, again, will take us to where we have to be in terms of energy balance. So again, if you have, just say that you have a calorie count of 1,800 calories, but your body requires 1,800 calories, you're going to stay pretty even. Or you're going to maintain your weight. Burn more than that 1,800, you're going to lose some weight. Take more in above that 1,800, you're going to gain some weight. Now, how much of that just depends on a lot of factors, like it says on the bottom there, but age, sex, pregnancy, do you have more muscle mass? Do you have a decline or a really high level of hormone function? Are you on medications? And then genetically, all of those factors come into play for, number one, the amount of energy you need in a day, amount of food you need, and what you're going to be burning and how well you're going to know whether you're going to lose or gain weight or maintain it. So a lot of these factors are very individualized, and it really becomes important to know each one of your individuals, not so much that, you're just kind of giving a cookie cutter set of, some sort of direction for them, because as trainers, you have this fine line between how much nutrition input you can give to people without giving a diet plan. So we got to be very aware of that, but also understand that we can give them information to know what their daily needs might be and how to over or under, indulge depending upon what their goal is. So lastly, to kind of build on very, very much what we just built on, the total daily energy expenditure, or what I call TDEE. It's composed of a lot of different things, but the main here is make sure you know this chart, because it's definitely going to be something that's going to be prepared for your test. Your resting metabolic rate, it's about 60 to 75% of your total daily energy expenditure, so it's the majority. The next would be what we would call your EAT or your NEAT. Now, EAT stands for exercise activity thermogenesis, so that means calories you burn during exercise. And then NEAT is things that you burn outside of that exercise, but more importantly, it's more like everyday, like activities of daily living, going to and from your car, things like that, but it's not structured, okay? And then the other part, which we call your TEF, or your thermic effective feeding or thermic effective food, depending upon what textbooks you read, that constitutes about 10%, and sometimes it varies. 5 to 10% is usually pretty close. But for test-taking purposes, know these numbers specifically, okay? So we got to be aware that, our resting metabolic rate is influenced by a lot of things. Okay, it's influenced by how much muscle mass we have, how much activity we do on a regular basis. There's a lot of factors that play into what your resting metabolic rate is. Okay, but it's a good indicator to know that it's the majority. So if you have a really high resting metabolic rate, then that means that you usually have a better chance of maintaining your weight than most others. But understand that there's bigger influences by, thermic effective feeding, which basically means that is the energy that you would need, okay? The energy, or not that you would need, it is the energy that is expended to digest and absorb the foods that you eat. So even though you're eating food and taking in calories, you still have to burn calories to break them down and to absorb them and to get them to where they gotta be. So it's very important to kind of gather all of that. So again, where are you in this perspective? Are you a very big exerciser? Because that 15 to 30% can have a massive influence on your RMR as well. And that would be the end of chapter 8. Really great information here. Really good information that will take you on if you wanted to learn more about. This is more exercise physiology in a nutshell, and how we work cellularly to break down our food products into the energy, or ATP, that we would need on a regular basis. So thanks again for watching, and I hope that you got something from this, because again, very important to understand that the metabolism component and the bioenergetics component, so that it can help you to grasp that material to make it so that you are basically able to just move people through the right energy systems through the proper exercise channels. All right, have a great day, and we'll see you back here for chapter 9.